Let's now study about logarithms. And the main aim is to eventually understand what a logarithm function is. But to start out, I am going to go through an explanation of what a logarithm is. And so, in how I see it, to understand logarithms, it's better to start out with the question as following. What power of base 2 equals 8? So it's a question. And then it's a question and we try to get the answer. So what power of base 2 equals 8? So the idea here is that as a picture that we should have in mind before we can give an answer to this question. Then think about it. It says right here in the question base 2. So that means 2 being raised to some unknown power. That's why it's asking, the question is asking what power of base 2 to equals 8. And so we're not looking for what equals 8. We're looking for what power of 2 equals 8. And so the part in here where I put the question mark is what we're looking for. And so again, that's the famous question for that. What power of base 2 equals 8? And so now quickly in a picture like this, then we can find out that the answer here is simply 3. The answer for that. Now anyone with a mature enough mental math mind and with just some minimal experience in power can quickly tell that 2 to the third power equals 8. And so there we go, we found the answer. So the main question I would like to circulate around here is the question about what power of a given base equals 8. And so what power of base 2 equals 8? So let's try again. Here I will bring up what power of base 5 equals 125. Okay, what power of base 5 equals 125? The answer to this question is in the picture as following. Base 5, but what power? That's why I'm leaving an empty box right there to equal 125. And so the answer we're looking for is to fill in here. And so now once we have that picture in mind, we can quickly find the answer here is, again, 3. It happens to be 2 questions. I ran into the same answer 3, but really I have no specific intention for having equal answers throughout the 2 questions. So now back to the 2 questions itself right here. Now I'm not any longer talking about the answers, finding the answer to the 2 questions here, but I'm looking at the structure of the question. Both of these questions share the same structure here. We're looking for the power of the given base. What power of base 2 equals 8? What power of base 5 equals 125? So this question can be symbolically addressed as a logarithm. So logarithm is, in my way of explaining things, in my way of explanation, a logarithm to me is a question. So here's how I see what power of base 2. What power is a logarithm? Base 2, I give the subscript 2. So what power of base 2, that's what this is, 2 equals 8. So now I put 8 inside the parentheses. Or sometimes we can skip the parentheses. Just log base 2 of 8. Okay, so now formally speaking, this is how we say it. Log base 2 of 8. That's how we say the symbol. That's how we pronounce the symbol. But what it means, this is the symbolic expression of this question. So a logarithm operation is a symbolic representation of this kind of question right here. Okay, and so that's why, for that reason, now now we can say that log base 2 of 8. Our mental math mind can quickly tell us that the answer is 3, as I already suggested the answer earlier. All right, so that's what to understand about what a logarithm truly is. And so in that way, let's apply our understanding into this case right here. The question again has that general structure. What power of base 5 in this case? So what power as a symbolic form is a logarithm. And so right now, so when I introduce, again, my intention here is that when I introduce the logarithm notation, I just want viewers to understand that this is a notation to represent a lengthy question. So, or it's a way to symbolically represent your question. And then that gives rise to a way to calculate, and the answer to the question is on the right hand side. And so now back to what I was in the middle of doing. Then what power of base 5? What power is a logarithm? Base 5 is indicated as the little subscript here. And so log base 5 of 125. So this entire question, what power of base 5 equals 125? That's how we symbolically translate that into a logarithm notation. And now we formally define a logarithm operation. Okay, so log base 5 of 125, that's how we pronounce it. Or sometimes, quite sometimes, we use the shorthand a little bit. I mean, just quite sometimes we skip the parentheses. So log base 5 of 125. And again, with the answer we have previously found, the answer to this question. So I want viewers, I want students who learn with me to understand a logarithm notation is a question. It's just simply a question. And then whatever comes out on the other side of the equal sign, that means it's the answer to your question. So the answer to this question of yours is 3. So that's what a logarithm is. And so in that reason, now in many algebra textbooks, and my aim is to give the understanding that's independent with textbooks. So now when you're reading into any textbook, any standard math textbook, specifically the algebra textbook, then you're going to find the following very common definition. So fundamentally, to understand, then I recommend understanding that like how I explained earlier. But then when it comes to a formal definition, then logarithm of a base a. So log base a of a number x. Okay. See, what power of a equals x? So that's why we say logarithm base a. Log base a of x equals a value y means the same thing as, or formally speaking, if and only if. And so now, as I was saying earlier, this, if we stick with my understanding as this as a question, seeing this as a question, log base a means what power of a equals x. So what power of a? And now think about the answer is power y, so a to the y power equals x. And this is the kind of definition that's very commonly seen in many standard algebra textbooks. And so the requirement for firing up a logarithm, or the requirement to be the base of any logarithm here, is that the base needs to be a positive value. All right, so log base a of x equals a value. What power of a to equal x? The answer to that is a y. It means the same as, see, what power? So the power here is y. A to the y power equals x. Okay. And now let's bring up another quick little problem to introduce another strict requirement of any logarithm operation. So let's say now I'm going to bring up a specific question. What power of base 1? So let's specifically look at base 1 right here. So what power of base 1 equals 2? All right, and let's see if we can find an answer for this. So what power of base 1 in my way of explaining things, in my way of the explanation, then what power of base 1 here is the same as the logarithm base 1. And we want what power of base 1 to equal to. Then that's how we're formulating the logarithm operation. So we're taking log base 1 of 2. But so that means in the way how the question is looking, what power of base 1? So base 1 raised to which power to equal 2. And so unfortunately we can't find an answer. There is no satisfying answer. So that means here we can't find an answer. And in a formal way of saying it, our answer here is undefined. And so for that reason, now looking back at our formal definition, we have to add in one more requirement regarding the base of a logarithm operation. So this is how logarithm operation is defined, where a is a positive number and a, the base of the logarithm, must be a value other than 1. All right, and so let's now do some more straightforward computation so that we can get used to the idea of operating with logarithm before we bring the concept into logarithm functions. So here I'm just going to say in this example, evaluate. All right. And so question A. Now I'm going to give log base 3 of 81. So I tend to use parentheses very carefully, but sometimes this can also be written as just log base 3 of 81, because with a simple notation like this, then we can skip the parentheses. But so now to understand, in order for us to find the answer successfully, see this log right here as what power? So what power of base 3 to equal 81? What power is that? That's the question to bring to your mind right there. And so the answer to there now is 4. All right, and obviously I didn't have to bring up any calculator. Anyone's viewing this video, believe in your own mental math skill right there. Your mental math skill is mature enough to understand this, and the answer can quickly come out being 4. So why is that? So this is because just a quick explanation, 3 raised to the 4th power, because we obviously we're asking what power of base 3 to equal 81, and so that power has to be 4. And so what fills in the box is 4 to equal 81, and that's what it is. In another problem, log base 10 of 10,000. Okay, so we say log base 10 of 10,000. So now I don't even need a calculator for this. Think about this. As I have explained earlier, log means it's a question. What power of base 10? So now have for yourself that picture of what power of base 10. That's what the log with subscript 10 is. What power of base 10? That can equal 10,000. Okay, and so now any of your mental math mind should be mature enough to find out that this is going to be power 4. And so the answer to this question, the answer to this logarithm, log base 10 of 10,000 is 4. And so now it's just an international convention. So here I have to highlight this as a convention. It's just something that agreed worldwide. Okay, just a convention, an international convention here, that anytime we are working with a log base 10, so supposedly we have to always indicate the base as a subscript here, but for log base 10 it is agreed worldwide that we can just skip the base. So log of 10,000, this is the same. Okay, it's the same as, and as a matter of fact, this one here is widely used instead of writing that as a log with a subscript 10. So it's the same as log base 10, 10,000. Okay, but instead of writing this way, the entire world out there is using log. So automatically, anytime we skip the base right here, that's automatically to be understood as log base 10 of the number. All right, and let's now talk a little more about the basis of logarithms. So now that you have seen log base 2 and hopefully have come to somewhere or some point of being fluent enough with understanding what a logarithm operation is. So log base 2 of 16, for example, this is the base, okay, and the number here, and the answer to that operation is 4, because we understand that as what power of base 2 to equal 16, and the answer to that, what power, that's power 4. Okay, we can also, throughout the earlier part of the video, I also introduced log base 3 of 81. Okay, and so this is asking for what power of base 3 to equal 81, and that power there should be, that power of base 3 should be 4 again. I also asked for log base 5 here of 125, and the answer back then was a 3. Now think about that again. It's the question, what power of base 5 to equal, that can equal 125, and the answer to that, what power, that's power 3. And so, and we have seen log, and now formally I'm skipping the base right here, but that's, remind yourself, this is log base 10. This is log base 10. Okay, so log base 10 of 10,000. The answer to that, well, to look for the answer successfully, we can think of that as a question, what power of base 10 to equal 10,000? And the answer is again 4. Now again, it's just by incidence, without any intention that I have a lot of answers being 4 here, but in the end, as you can see now, is that back to the definition as I wrote earlier, then all of these bases here are required to be positive. Okay, so the base right here, anytime we're looking at given a logarithm base a of a value, then the base has to be positive and other than 1. So, but that's all I'm saying. We need a base being positive and other than 1. So that means if we expand our understanding a little more, then outside of these nice whole values acting as the bases, we can also work with log base pi, for example, of a 2.71934, something like that. So this, of course, I'm not saying that we can mentally find this problem, but at least we can still understand that this will have an answer. It will have a definite answer. And the answer to that means it's the answer to the question, what power of base pi? Because pi raised to what power? To equal 2.71934. Okay, and so I will show the calculator trick a little bit later on for how to get something like this, because of course a problem like this, to obtain that answer, I'm not saying that we cannot do it, but obtaining an answer for a logarithm operation like this is of course way beyond our mental math capability. Or we can find log base 0.5 of 4. Okay, and so the base here is still completely legal because it's a positive value, and also it's a value less than 1. And so now, as I'm teaching this, I am more experienced, and so I can tell that the answer to this is -2. But you are not required, and no one viewing this video is required immediately to know how we get this, and it's not really a mental math trick or anything like that. Eventually experience will build with you, and you will get better at doing these. But the way I see this is base 0.5 raised to power -2 equals 4. And here you can use a calculator to check for this, to verify this. All right, and now immediately before I start introducing the concept of a logarithm function, now I am going to start doing this. Let's say I'm going to specifically stay with log base 2. So log base 2. So 2 is the base. So that's how I say it, log base 2. But it means what power of 2. And how about I'm going to choose a number. So log base 2 of 32. The answer is 5. Same log base 2. Let's do another simple calculation. Same base now, purposely. I can ask for log base 2 of 4. So to understand, to successfully get the answer, understand this as a question again. What power of base 2 equals 4? So what power is that? Power 2. But so far with the two quick computational problems, we can see that with the same logarithm being previously chosen to work with, we can apply the logarithm base 2 on different numbers already. We can also do log base 2 of 16, and the answer is 4. Because now if you're asking yourself that question, you can easily find the answer. What power of 2 equals 16? The answer must be 4. And even when we're looking into something that beyond our mental math skill, but the kind of work exists out there. Log base 2 of 5. I will, again, as I said, I will show the work, how to use a calculator to perform the calculation, but right now our mental math capability cannot get us the answer, but it's an answer that exists out there. But now see this as a question. What power of base 2 equals 5? And that power right there is of course very challenging to our mental math capability, but we can use a calculator, and I will show that to everybody shortly. But according to my own calculator right now, my own calculation right now, the answer with a calculator is approximately, because it's a lot lengthier than that, 2.32192, and a lot longer. So the idea that I'm bringing up now is that now we can see that putting together with all of these simple calculations, they're all on base 2 of a logarithm. Then we can see that these different numbers that we're changing here can be regarded as the inputs of a variable of a function that now we call log base 2 of x. So generally we can regard to any of these different computational problem as a generally as a function. So here I can define here a function f of x equals log base 2 of x. So that now if we look back into this first computational problem, log base 2 of 32 truly is f of 32. If we're now looking at this computational problem that we did earlier, log base 2 of 4, the output here, so this is now input being 32 and the output was 5 here. Now the output is 2, the input there was f of 4. So my point again is that once we now recognize that generally we can define a function that takes logarithm on any value x, then any of these output, any of these final answers here can be understood as the function output for our previously defined function f of x. So here 2 equals f of 4, or f of 4 is the same as log base 2 of 4. 5 is the output for f of 32, and by previously defined f of x is log base 2 of x. And so 5 is the output of f of 32, or we can say that it's the output for log base 2 of 32, and so on. And so here this is the same as the function evaluated at 16. And this ugly looking number right here, I had to use a calculator because it's way beyond my mental math skill. But this is f of, see, log base 2, so that's our logarithm function. But now this is f of 5. So what we have here is our first look into what's so-called, this is a logarithm function. All right, so now we are ready for looking into the what's so-called logarithm functions. Okay, and so as a formal definition that can be found quite commonly throughout most of the standard algebra textbooks, that a function f of x that's given by f of x equals a log with some given base right here of x is called a logarithm. It's a logarithm function, base a. And from here, where base a is a positive value and we are only working with base a other than 1. And now let's look a little more into about the inputs of a logarithm function. So now we know that a logarithm function is required to be on a positive base. So let's look right at base 3. How about that? For example, so log base 3 of so let's now look about the inputs. Can we perform the log base 3 operation on input being 27? Notice it's a positive number. Sure, yes. The answer here. So now if you ask yourself that question, what power of base 3 equals 27? Can we find an answer to that question? Yes, we sure can. The answer is 3. The same logarithm here, we can switch to a different input. So now I see this as a function. The logarithm base 3 is a function, and that is an input. So far in the first problem that I brought up, it's an input being positive. Now, same logarithm. We can put in a 3.741 log base 3 of 3.741. Can we find an answer for this now? An answer to the question of what power of 3 equals 3.741? Of course, the answer is beyond our mental math skill, but a calculator can get us an answer. So in other words, we still have an answer. Formally speaking, we still have an answer that's defined here. But now, think about another different inputs. So even with an ugly input like this, we can still have a successful output. Either we can do mental math, or we can just use a calculator to get. So that's why I didn't use a calculator. So I generally refer to this as a defined value. We have a value successfully that we can successfully calculate. But now, if we're looking at log base 3 of negative 2. So now if I use an input being a negative, let's see what happens. Again, can ask yourself that question. What power of base 3? What power of base 3 to equal negative 2? And so now I have to address this a little bit, but if it's me teaching logarithm, then I always teach logarithm after teaching about an exponential function. And so if you recall, once you have arrived at my video lesson for logarithm, then I'm assuming that you have watched my other video lessons on the exponential function. Then an exponential function, the negative 2 in our case here, is an impossible output for, because here if we're looking at an exponential function 3 to the x, then the output can only be anywhere, can only be a positive value. But here we particularly want the outputs for this exponential function. What power of x, what power of 3 here to equals negative 2? So this is entirely impossible. It violates the what's so-called the range, the output range of our exponential function, 3 to the x. And the reason I bring up 3 to the x as an exponential function here, because here we're looking at base 3. And so in that case right here, having a negative input for a logarithm is going to give us an undefined answer. And that's what my point is. And now what about the same base on the same logarithm? But I'm going to call log base 3 of, how about 0? So I purposely try through different inputs, some positive inputs and some negative inputs. And we ran into an undefined answer. And now what about an input being 0? So log base 3 of 0, to find the answer to this, once again, imagine that question. What power of base 3? So it's now in exponential form right here. What power of base 3 to equal 0? And again, remind yourself what I wrote down earlier. An exponential function output, because now the input 0 here is acting as the output once we have put our understanding as an exponential form right here. And so doesn't matter what power that is, but the output for an exponential must always be positive. So we can't even have, it's impossible to have an output being 0. So in other words, we won't be able to find a satisfying answer. What power of 3 equals 0? So in other words, here we have another undefined answer. And so in that way, back to this definition, right out from the definition, once we have defined a function f of x to be a logarithm function base a, then on any base, on any logarithm of any base, the domain, because earlier we were just investigating the different values of the input, so that we can track down where the domain of our function is. So the domain of logarithm function is anywhere greater than 0. So 0 to positive infinity in interval notation. And it's not even going to include 0, so that's why I'm using parentheses here. And so domain is the set of all input of the given function here where it's possible to substitute in. And so throughout my a few demonstrations, I showed that we can only give a positive input to any logarithm function, not a 0, not a negative. And now, after we have had some hopefully thorough enough understanding about a logarithm function, a general logarithm function, then let's spend some time talking about the logarithm base e in our video lesson here. And so I have introduced in some of my other video lessons that pi is a constant that has been known for a long time, and approximately it's 3.14 and a lot longer. So it's one very well-known constant in the math history. And so in the modern math, there's another constant similar to pi, and that other constant, I'm now bringing it up, is named E, and the value for this 2.718 and a lot longer. And in some other video lessons I have already shown, I also show the calculator trick to get the actual lengthy decimal expression of this value E right here. But usually for anyone, that we can just simply keep in mind that E is approximately 2.718. So for now, our learning has just begun. So keep E as a constant that is similar to pi. It's just some constant that we just have to know. Of course, it came much later than pi. Right? Pi has been known for a very long time, but E has just been recognized for about a couple centuries or so. But now, how I see it now is that since E has value approximately 2.718, so apparently it is a positive value and other than 1. And so in that way, it is completely possible to define a logarithm, because again, as we have seen earlier in this video, that as long as we have a number, a value other than 1 being positive, and doesn't even have to be a whole number, then we can define a logarithm. And so we can take log base E of a number. So let's say, generally speaking, let's say log base E of a number x, of a value x, or of a variable x. And so this is called log base E. That's how we pronounce it. Log base E. That's the most natural way. But now a more common name, a more special name. And surprisingly, as we define this logarithm base E operation, then eventually as math evolves, then this logarithm base E becomes even though starting out as a special log, but now it becomes the one that grabs the most attention from people. So when it's log base E, we have another nicer name, the natural log. And when we say natural log, people will understand that it's log base E. And when it comes to log base E, instead of writing log with a subscript E right here, people worldwide is using the symbol ln of x. So this is ln of x is the same. It's the same as log base E of x. But this is the formal notation for log base E, and entirely replaces log base E notation. So anytime now on any standard calculator, you will see a button somewhere that says ln. That is log base E of whichever number we're about to calculate for. And so now in that way, a function f of x that's given by the following definition: f of x equals natural log of x, or ln x. This function, as a definition, is called the natural log function. And again, as I have explained earlier, once we see ln of x, we will automatically understand that this is log base e. So natural log function is the formal name, but that is automatically understood as this is the logarithm base e of x. And so when it comes to calculating an output value for logarithm base e, for example, natural log of 2, the answer means we're looking for what power of e to equal 2. But doing this, we will need a calculator. So again, it's one of those problems where it's beyond our mental math capability. So we will need to use a calculator, and I will shortly I will soon bring up the calculator screen so that anyone can learn how to calculate a value like this with a calculator. And we definitely need a calculator. And so we can, so natural log of 5, yes, we need a calculator. It means log base e of 5. And so almost none of the evaluation work for natural log can be done mentally, because the base e itself is not a whole value at all. And some simple one that we can quickly understand is that log base e, or natural log of e itself. So if we purposely take that e and evaluate log base e of e, then think about that what power, it means what power of e to equal e. And so now this one here is one of the one among the few occasions where we can actually use some mental math right here to quickly find the answer without using a calculator, because e raised to the only power, the first power, to equal e. So the answer to this is 1. Or in some other occasions where the problem can be as simple as natural log of 1, then this is the same as it means the same as log base e of 1. But what power of e to equal 1? What power of e equals 1? And so according to the rules of algebra, a non-zero value raised to a power 0 will always equal 1. So the answer to this is 0. So these are pretty much the only two occasions where we can mentally calculate the output value for our natural log function. But for the rest of those, we are going to have to use a calculator or a technology of some kind to help into the calculation work. All right, so let's talk some more about the basis of logarithm. So we have learned. So at this point, we have learned that as long as we have a positive value and other than 1, then we can set up a logarithm in respect to that given base right here for a number, for a value. And so this is the general general notation for a logarithm base a. But now, as we have now looked through a few problems, then when it's log base 2, then we have to write log with a subscript. When it's log base 5, we have to write log symbol with the subscript 5. When it's log base pi, we have to write the log symbol with the subscript indicating the base. Because so far I'm using those bases other than 10 and e. And so now that means when it's the special one, log base 10, then we have seen earlier that now we're going to write this as just log and skipping the base. So skipping the base is log, the log symbol with skipping the base, this means same as log base 10, or log is the same as log base 10 of x. And so now additionally, we've just now learned that when it's another special base, log base e of x, this is a special one, is now the same symbol. So here I'm talking about how different bases can change the way how we write the symbols, the notations for logarithm. So log base e is the same as ln of x. And so log base 10 is special, we skip the base. Log base e is special, we don't skip the base, but we write it as a shorter symbol, ln of x. Any other bases, like base pi, base 5, base 2, base 2.5, base 0.5, any other base other than these two special bases. So generally speaking, log base a of x, we must indicate the base when the base a is other than e and 10. And we're now going to learn how to calculate a logarithm value using the calculator. Now I'm using a standard TI 8384 calculator, but any basic calculator on the market out there comes with the standard logarithm feature. So you can see how I'm doing it here and apply that to your own basic calculator, because I believe it should have your calculator outside of these TI 83 or 84 should have the similar functionality. So now any calculator, including the one I'm using here, comes with, you see the log right here, that's log base 10. So quite directly written, and also comes with an ln key right here. That's for log base e, as I have explained about these logarithms throughout my lecture on the writing board. And so let's say if we want to do a calculation for log base 10 of 5, the reason we're doing a problem like this, because this is a logarithm where it will have a value, but we won't be able to do the mental math for this. So we definitely need the calculator to help us. So this is, again, this is log base 10 of 5. We skip the base right here. And so to do this work right here on the calculator, we just simply, now with this particular calculator I'm using, then we hit the log key, and so it brings out log, that symbol, that notation, log base 10 in parentheses, and now we put in 5, and that's what it is. And so we get the value being 0.69897 and a lot longer. So log base 10 of 5 is 0.69897 and a lot longer. It all depends on how far the rounding requirement, the problem that you're working with requires. And so now, if we're working with a different problem, for example, ln of 2, for example, okay, and as I have explained earlier, aside from natural log of e or natural log of 1, any other natural log problem requires some assistance from the calculator, because we just can't do that. We normally can't do that with our mental math capability. And so only be aware that this is log base e, or we call it the natural log of 2. And so to get the answer of that on my calculator, I'm going to hit the ln key, which is the button, the feature designated for log base e, and now I'm going to enter 2. That's what it is. And so natural log of 2 is 0.693147 and a lot longer. 0.6931 47 and a lot longer. But now let's have a closer look at the calculator screen right here. So on our calculator, and it is the same with any other calculator, we just don't have a button anywhere on the keypad here for a log base 2, for example. We won't have a button for log base 5. We won't have a button for log base 0.5. Any calculator on the markets out there only gives either a natural log, log base e, or a log base 10. This calculator gives both. Some calculators only give one of the two here. So how can we calculate log base 2 of 9? Because this problem is another logarithm problem where it's beyond our mental math capability. We know with mental math we can do log base 2 of 8 because power 3 of 2, power 3 of base 2 equals 8. So this answer is 3 quickly. We can find that easily with our mental math. But now log base 2 of 9, we know the answer will be out there. But how can we find that on our calculator? So here's the trick that we can do in the calculator. So on my calculator, notice we're currently doing log base 2 of 9. So to do that, we have two choices of the workaround. So on the calculator, anytime it comes to calculating the log other than base e and base 10, we have to do a workaround. So let's now make a choice to stick with log base 10 right here. So I'm gonna go with log base 10 for now. So I'll press log base 10 of 9. So notice that this 9 came out from the value that we're calculating log from. And now back on the calculator screen, after typing in log base 10 of 9, I am not going to hit enter yet. I am going to divide. I'm going to divide log base 10 of 9 by, again, as I said earlier, this is a choice I picked right here. I go with log base 10. So I'm also going to divide by log base 10, but this time I'm taking in the denominator. I'm taking log base 10 of 2. So quick explanation, this 2 came from the base of our original log problem. So our original log problem here is log base 2 of 9. So it looks like the way to do this on the calculator is to one choice. As one choice, we go with log base 10 with the bigger number and divide that by log base 10 of the smaller number of the base. And using log base 10 is a choice. So now on the calculator, we are ready for hitting enter. Hitting enter, we have 3.1699. So as I keep emphasizing earlier, using log base 10 is a choice. So that means we can also, right from the beginning, I could have also used a natural log base e as another choice. And believe me, it will come out the same answer. So let me quickly do a work right here. So if I chose from the beginning to use ln or log base e, then we can go ln of 9. Again, the 9 here is the number that we're attempting to find the logarithm. And from there, after closing the parentheses, I'm going to divide. So natural log of 9 divide by natural log of 2. And again, the 2 here came from the original base, the base of the original problem. And so now you can see that the way to set up the problem is very similar. It's just the same work right here. We have a choice between using log base 10 or log base e. And let's now hit enter and compare the answers. The two answers are exactly or identically the same because it's the same answer. So this is a method that was originally proven algebraically, but now in these modern day, we can just use that as a main trick to get around to find the value for any logarithm with base other than e and 10. So now back on my writing board, I could have also done the same as ln of 9 over ln of 2. You don't need to do both. Just pick one of your log choice like that. And again, because the whole reason here is because any calculator on standards only offer the most log base 10 and natural log base 2. But now as far as the answer, this is going to be 169,925 and a lot longer. And now we can study the graph of a logarithm function. So on my computer screen here with Desmos.com, the graphing calculator that I use as my favorite graphing device, then I have already prepared a function f of x equals log base 2 of x. And so we are going to, again, use Desmos to construct a table of value, and I'm going to go as briefly as I can. And so when our function is log base 2, and recall from our previous understanding that for any logarithm function, base 2, base 10, or base e, base 5, as long as we're looking at a logarithm function, then the domain is anywhere between 0 and positive infinity. So what it means here, the reason I have to mention this before we getting into the graph, studying the graph of a log function, or in specifically here the graph of our log base 2 function, is that we can only choose the x values that are positive. We can only choose the x values, the positive x values. Okay, and so, and for a few times I am going to swing back and forth between the Desmos graphing calculator here and the TI-8384 calculator, so viewers can have additional opportunities to learn how to calculate the values of a general logarithm on a calculator. So now I'm going to enter, remember, positive values only. So I will put in how about x equals 1, and the function output. So this means log base 2 of 1, and the function came out with, on my table here, Desmos came out with y equals 0. So this is the y value right here, and we came up immediately on Desmos screen here a point right at 1, 0. Then now I can try with x equals 2. And so x equals 2, and these are easy values that we can also do the mental math here. And so when x equals 2, it means log base 2 of 2. And that means we can see that what it means now, the answer here means 2 to the first power equals 1. Or remind yourself that this log base 2 means what power of base 2 equals 2 in this case. So the answer to that has to be 1. And that is what it is here. And I can put in another value. Let's say 4. And now, once again, if we're looking at this log base 2 of x as a function, then when x equals 4, it means log base 2 of 4. But log base 2 of 4 means we're trying to answer the question, what power of base 2 to equal 4? And that power is 2. And so now we have a plotted point, a coordinate point 4, 2 on the grid right here. And these are the other points that popped out. And so far we can see that from the left to the right, these points are forming into a rising path by far. And it doesn't look linear. It doesn't look to go in a linear path right here. It starts to bend. But let's put in more points, more x values. So here, what about we're going to put in x equals 8. And so Desmos quickly came out with y equal 3. And looking at this as a log base 2 as a function, looking at log base 2 of x as a function, then when x equals 8, we're looking at log base 2 of 8. But log base 2 of 8 means what power of, means we're trying to find the answer of what power of base 2 to equals 8. And so now that means the answer has to be 3. And so now we have another point that popped out right here. I can also try with x equals 16, and we have a point way out here. And any of these, I purposely chose the easy values that we can do a calculation without a calculator. But what about when x equals 6? So Desmos can do that, but this is beyond our mental math capability. So let's see how the calculator can get this done, how we can use the calculator for this. So namely, this is log base 2 of 6. So now on the calculator, on the TI 8384 calculator, we can go ln of 6 divided by ln of 2. Recall that we never had a direct button for log base 2 on any of the standard calculators. So we have to do that trick by making a choice first, making a choice between going with log base 10 or natural log, and we're taking natural log of the value and divided by natural log on the base here. And so now hit enter. We have that answer that agrees with the value that came out from Desmos calculator right there. All right, so how about let's try a value that's in this small interval between 0 and 1. So recall that we cannot have an x input that is equal 0 or the negative. So we can only take the value that x values that are positive. So I'm going to go with positive 0.5. And so now quickly Desmos gave a negative 1. And let's quickly swing back to our TI calculator and verify. So this means right now it means as far as the operation we're doing log base 2 of 0.5. So log base 2 of 0.5 on the TI calculator, we can go, I can make a choice for using ln. So ln of 0.5 divided by ln of the base. And here is base 2. And so the answer here is negative 1. And that's which agrees with the answer that came out from Desmos. And so now I'm going to put in another value that's less than 1 inside of this interval between 0 and 1. How about 0.25? And you can see that I purposely chose x values that keep getting closer and closer to x equals 0. And so the output here came out negative 2. I can try another one. How about 0.125? And we are looking at y equals negative 3 correspondingly. And that came out with the point right there. So these are the points. So now with these points right here, we start having a better recognized shape right here. So obviously it forms into a rising path again from the left to the right. But it looks like all of these points by far that we have made, they stay completely on the right hand side of the y-axis here. All right, so now let's put the actual graph on, and then we will get ourselves convinced about the shape of the graph here. So here it is. That's the shape for our log base 2. That's the graph for our log base 2 of x right here. All right, and now once we are familiar with our first graph of a logarithm function, and specifically that was a log base 2 of x. And so now let's study a little more to get to understand more details regarding the graph of a logarithm function. And so on another tab right here with my Desmos graphing calculator, so we have already seen the graph for log base 2 of x, which is right here. It's a one-way graph growing from the left to the right, but the entire curve itself stays to the right-hand side of the y-axis. And that's our graph for log base 2 of x, which is being in red color right here. So we have also studied previously what it means by having a natural log of x. And natural log of x is nothing but just log base e, where e itself is a very lengthy decimal value, 2.718 and a lot longer. But in the end, being a logarithm, then let's see what the graph of that looks like. So now I'm going to show the graph for natural log of x, and it's the one being displayed in blue color right here. Okay, and so with the two graphs being displayed here by far, then I can see that the two graphs have the same fundamental shape. It's a graph. It's a bent curve that's rising from the left to the right. And both of the blue and the red graphs are completely on the right hand side of the y-axis. Once again, simply because if I was sketching the graph for natural log of x completely from scratch by choosing x values, again, I can only choose x values that are positive. And now let's show the graph for log base 5. So log base 5 is being displayed with decimals here in green color. So decimals has a really nice color coding feature for these graphs here. So again, I am seeing the very similar fundamental shape here. It's a bent curve. For now, let me hide away the other curve here. So only the green, which is the graph for log base 5 of x. And you can see that the graph itself is again in that fundamental shape with one way rising from the left to the right. And the entire green graph itself is only on the right hand side of our y-axis. And now let's put the other curves back. All right, and so last one on the list here to see, this is again no base indication, so that means it's log base 10. So log base 10 of x. Let's see what the graph looks like. All right, so now the graph for log base 10 of x on our list is being displayed in purple. And so let me now quickly hide away the other graphs and only keep the purple one right here, which is log base 10 of x. And you can see that again, that same exact fundamental shape came out from log base 10 of x. And so it's a one way rising from the left to the right, and the entire purple graph is being only on the right hand side of the y-axis. And now let's put the other graph back. Now when we are on a TI calculator, and really it's for any standard graphing calculator, not only the TI 83 and 84 calculator, then sadly, as I have discussed earlier, these calculators do not offer any other logs aside from log base 10 and natural log. And so we are a little bit limited here. I'm not saying that we cannot graph, but it takes a lot more work around. So here on the TI 83 and 84 calculator, or any standard graphing calculator, I can only show how to make the graph for log base 10 and natural log of x. And so again, we're going to go to, on the TI 83 84 calculator, I am going to hit y equals to enter the function. And so I'm going to choose to enter a logarithm for y1 right here. Let's say log base 10. Now, the variable buttons, we're going to stay with the traditional, on the calculator, we're going to stay with the traditional variable, which is x. But the variable button is the x button right here, not the alphabetical x button. So we're going to close that parentheses and hit enter. And now after hitting enter to exit out of that line right here, the next thing to do to see the graph is just hit on the graph button. And now we can see that line, that curve again, that looks just like the one with that decimals give. And we can, anyone viewing the video here can search in your own manual or search the web for, for some kind of manual to know how to operate with the zoom. We can just, and to understand a little better about the zoom feature. But here, when you click on zoom, we can zoom in a little more. And now as we zoom in, then the graph, the calculator is able to show a little more. So of course, the graphing feature of the calculator, of a standard graphing calculator, is not as advanced as the graphing functionality with decimals, and that's why decimal has become my favorite graphing device in a long time. But that's basically how we can get the graph on a standard graphing calculator, and this is specifically log base 10. And so what about log base e right here? I'm going to go back to the button y equals, and let's put in log base e, or natural log. So the key is found right here. So natural log of x with the x button, close parentheses. And now if we want, so that means now we have two functions to be to display the graphs. And so if you want to go with that way, then we can just now simply hit graph. And now two functions, they natural log of x is this graph in red right here, and the other one is log base 10 of x in blue. And so now, so far, after investigating a few different graphs like that, then we can start drawing out some generalization here. Now it looks like I so far focused on those logarithms where base was a value that is greater than 1. And so when base is greater than 1, then it looked like what we have seen was fundamentally the shape where it's a rising bent down curve, and rising in that way right there. The rise was quick when the graph was still below the x-axis, and then the rise becomes slowing down when the graph goes above the x-axis. But that's generally the fundamental shape for any log base a of x function, where base a is a value that's greater than 1. And if we're looking back on the Desmos graphing calculator, all of these graphs where the base is a value greater than 1, they all go through one common point right here, 1, 0. And so now that's something that's worth to take note about. So this point on the x-axis where our graph crosses through, our logarithm graph crosses through, that point is famously known as 1, 0. And of course, because the domain of our graph, because the domain of our function is only anywhere from 0, between 0 and infinity. So that's what explains for the graph is entirely to the right hand side of the y-axis. So the graph itself won't even hit the y-axis at all. It won't even cross the y-axis. All right, and now let's investigate a few graphs where, now you can see on my list here I have prepared a few logarithm function with the graphs hidden, so that we can see that these are the one that I'm about to show the graphs, but the bases here are all, they're as positive again, but they're less than 1. So let's look at how about log base 0.5, or this is the same as log base 1/2 of x right here. And now I'm going to quickly ask Desmo to bring up the graph for this function, log base 0.5 of x, and now we're looking at a graph that's falling. So unlike the case where the base was a value greater than 1, now our graph is falling. But it looks like it's still going through that point. It's still going to cross that point on the x-axis at the 1, 0. And again, the graph here is entirely, the entire graph here in red is completely on the right-hand side of the y-axis. Okay, so I just now put it in a little bit of a closer zoom right there. So, and once again, the reason for this is that for as long as we're looking at a logarithm function, the domain for x must be positive values only. And that's the reason why, that's explained why we only take x value that's, to the right-hand side of the y-axis, or the entire graph itself is completely to the right-hand side, on the right-hand side of the y-axis. And so now that this red curve right here, this red bent curve is, and it's a one-way falling. So it's for log base 0.5 of x. And so now let's bring up the graph for log base 0.2. Now, so base 0.2 is smaller than base 0.5, but in the end, these are all bases that are below 1 right here. So let's look at the graph. And so now we have another fundamental shape again. It's a falling one way, completely on the right-hand side, the whole graph in blue. This is the graph for log base 0.2 of x. The whole graph is on the right-hand side of the y-axis, once again, because that needs to be consistent with the domain of any logarithm function. And the graph, again, this graph here in blue passes through the x-axis at that point 1, 0, right on the x-axis right there. And now let's put in the graph for log base 0.1, another base value where it's quite less than 1 and closer to 0. And so this time we're looking at the graph in green color right here. Okay, and so again, let me quickly hide away these other two graphs, blue and red, right here, and only keep the green, so that we can see that we have changed the bases, but in the end, the graph of a logarithm function, log base a of x, where a is a value less than 1, is in a fundamental shape right here. It's a falling down from the left to the right shape, and the entire graph is on the right hand side of the y-axis. And again, this graph goes through the x-axis at that point 1, 0. And so let's now put it together with all the other graphs. And that's how we're looking at the graphs of a logarithm of x, logarithm function of x, with the base less than 1. And so now, generally speaking, in the case where our base is a value that's positive, of course, but less than 1. So now allow me to write that we're looking at a base where it's anywhere between, a base value anywhere between 0 and 1. Then one common generality that we have drawn out from the graph, the graph we study, was that the graph is a curve that shows a falling from the left to the right. And here's the x-axis. And the graph for log base a of x, where a is a value between 0 and 1, passes through the point 1, 0 again on the x-axis. And that's the y-axis. And again, and we can also see that the fall was quite steep before the graph hits the x-axis. But after the graph hits the x-axis and falls below the x-axis, then the fall up on the graph is becoming slower and more slowly and more slowly. And so now, specifically, since sooner or later we will turn most of our focus to the special logarithm that's called natural log of x, which is understood as log base e. Then, even though being a special logarithm because it has so much applications out there, but in the end, the base itself is a value that is approximately 2.718 and being greater than 1. So I am expecting that the graph of natural log of x, and we actually have seen that throughout our Desmos demonstration. So the graph for natural log of x will definitely be this shape right here, where it will cross at 1, 0, and it will carry out that general shape like any other logarithm. And so this can be, and of course, forgive me that I'm being off scale here, but that's being on scale is not the point. So the graph for natural log of x should look like that as well, just like any other log base a of x where base is a value greater than 1.